Alright, so this is a very quick video on CAN messages, how we hack CAN messages and how we're able to send our own ones. It's really important for EV conversions if you're using a more modern vehicle, anything beyond 2001, because a lot of the information that's displayed on things like the instrument cluster are sent via CAN messages. So we've got a CAN board just behind the computer here. That's connected to this instrument display. It's from a W203 Mercedes, about 2008 to 2011. So let's have a look. We've got SavvyCan, which is the program we're going to be using, and we've connected the board, which is one of Damien Maguire's VCU boards for the Nissan Leaf, which we've loaded up the SavvyCan code onto. We just connected it here. You can see the board's connected, and it's got 3 CAN buses, although there's only 2 really in use. We're going to be using CAN bus 0. So that's the board connected. So we're going to start by playing some CAN information through the display itself, so we can see what the messages look like, and then we can start to tinker around with them, see if we can find the messages we're looking for. Today we're going to try and see if we can manipulate this RPM gauge here, so we can get the tachometer to read whatever information we want it to read. This is really important because once we understand the format of the CAN message, then we can create our own CAN messages in our VCU boards or whatever you'll be using in order to allow your instrument display to show the information you're trying to produce. So to start with, first a big thank you to Jason Wright. He recorded a load of CAN data from his Mercedes SLK using SavvyCan. So we're going to start by replaying that information back through this display here. His SLK is a 1998, so it's got less CAN information than this W203 would be expecting to find, because it's obviously from a newer vehicle. So for that reason you might see the information you want to see, but you might expect to see a few of these sort of DTC messages, basic error codes. So things like you're going to see an check engine light show up. The other things to think about are that I'm not going to be recording the body CAN, so we're not going to be playing back any body CAN information. For those of you who don't know, cars usually have at least 2 CAN buses. They'll have an engine CAN bus, which is quite important. It's the main CAN bus, obviously, that's used for things like running the engine, ABS units, and all the really critical CAN information that a car would need to use. Body CAN is for the less critical information. A lot of it's still really important. So things like the headlight display, where, as you can see, that's showing full beam right now because that's the default on the display. If the sensors were to break, it would just default to showing you the full beam light. Things like the parking brake, it doesn't have any information about the parking brake right now. So as there's no CAN information going through here, you can see it's lit up like a Christmas tree. But even when we play the engine CAN data through, if it's not getting that body CAN, things like the fuel gauge, they're just going to show basically zeros, and in this case we're going to see a few of them are going to default to the lights staying on. So let's have a go. I'm going to start by going to the playback option, and I'm going to load the information that Jason's very kindly recorded for us. In this case it's the information from when he was driving. My cat's decided to join us as well. So if I start by playing back the information that he's recorded, first thing you're going to see is a load of those lights go out. So because his is a manual vehicle, things like the Speedtronic CAN information isn't there. So that's obviously something from like a Tektronix gearbox that obviously would tell you what gear the car is in, but because it's a manual, it doesn't have that information. So you can see now, obviously Jason's been out for a drive. You can see there's his tachometer, he's revving his engine, and the vehicle's starting to move under its own power. My cat's really going to be helpful here by blocking the speed information, but there you go. You can see that the tachometer's moving as the engine's revving up. Vehicle's up at 30 miles an hour, and now it's back down to 20. So he's out on a drive. If we have a look, you can see already the trip is now starting to count up as well, which is great. So all of these CAN messages are being sent right now. If we have a look at what that looks like in SavvyCan, we can see here is a big trickle of CAN messages that are being broadcast at quite a high speed in order to give this information to the instrument display. So it's seeing what it's expecting to see. These would normally be produced by things like the engine ECU, the ABS unit, but obviously now they're being produced purely just through this board, which is just replicating what it saw. So I'm going to stop the CAN messages now. If I just hit the stop button here, you're going to see that the instrument display is all going to return to zeros. So now we have a load of CAN messages, and we know that they do something with the display. What do they do? Well, let's find out. So once I start playing them, what I'm going to do to begin with is deselect all of them. So there's that Speedtronic warning again. Let's turn that off. Let's start turning some on. So if I pick one that I know what it does, the the 208 message, you'll see all of a sudden we start to get speedo information. So right now there's a speedo, 20 miles an hour, and it's moving around quite happily on its own. Everything else is quite unhappy because that's the only CAN message right now that's being broadcast. So let's try adding the tachometer. So I know this is the 308 just because I turned it on before, and all of a sudden we see RPM. You can see there's still lots of unhappy information here, things like coils, the check engine light, ABS, everything's pretty unhappy at the moment. But those two messages give you your speed and your tachometer. If I turn off the 208, you'll see we'll just get the tachometer. So speedo's gone, but we still have tachometer information. So now we've isolated a CAN message. We know that the 308 message is the tachometer. It's probably worth mentioning as well, you can see each of these codes, these CAN messages, have a format, and you can see that they say 0x308. Well, what does 0x mean? If you're not familiar with hexadecimal numbers, very briefly, firstly watch The Martian, it's great. The main thing to know about hexadecimal numbers is that we use the decimal system because we have 10 little digits on our hands, so we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hexadecimal number format is more compatible with computer code because obviously computer code is in ones and zeros because of all of the gates and processes, blah, 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 blah. The main thing to know obviously is that with hexadecimal numbers, they don't go from 0 to 9, they go from 0 to F, which is really helpful. So if you think about it from how the numbers would appear, they go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So F is the number which would be representing 16, except it would be 15 because 0 is also a number. So those are the 16 numbers in a hexadecimal number format. How does that appear in a CAN message? Well, first of all, 0x308 is 308 in hexadecimal format. 0x means this number is in a hexadecimal format, so it's not actually 308.
To find the decimal value for 308 in hex, you can use an online calculator. If you enter the value 308 and convert it, this tells us the decimal value equivalent is 776.
So I've paused the CAN messages right now. We were sending the 308 message. Let's have a look at how that appears. So picking one at random, we have a 308 message here. As we say, that's its hex ID. Don't worry about these two for the moment. This is just different formatting for CAN messages. Direction, it was transmitted by the VCU board, which is behind the laptop here, into the display. It's on CAN bus 0 because right now everything's connected to CAN bus 0. The board itself has two CAN buses, so if you wanted to connect one to, say, the inverter and you want to connect one to everything else, you could do that. If you wanted to connect one to the inverter and all of your engine information, you could do that as well. But the important thing to know is obviously it's being transmitted at a particular speed. So normally engine data is transmitted at 500 kilobytes per second because it's really important stuff that the car needs to read quite quickly. Less critical things like the parking brake, it's obviously still very critical, but it doesn't need to be detected rapidly. So for that reason, it's sent at 125 kilobytes per second on some vehicles. Some of them it's like 83 or less, but obviously that can change from car to car and manufacturer. So in this case, we're not looking at body CAN, so everything we're dealing with is at 500 kilobytes per second, and right now everything's being broadcast through CAN bus 0. The length of the message, well, normally a CAN bus message is sent in 8 bytes, which is obviously these pairs here. You can see you've got 8 pairs of numbers. They can be longer, it really depends on certain messages. They can be shorter, you sometimes see 7 byte length messages, but again quite rare. ASCII is just a different way of reading the message in a different version of computer code. So really what we're more interested in is the data in the message itself. So let's have a look at that. We've got 8 individual bytes which each have their own information written in hexadecimal number format. So you'd see the number 80 and you'd be forgiven for thinking that 80 means 80. It doesn't, because hexadecimal numbers, as we've already said before, they go from 0 to 15. So when we get to a number 3, it's just 03. So that's 3, whether it's in decimal, hexadecimal, whatever. But of course, if we get something like 0F, then that's 0 plus 15, so we know that that's 15. So what happens with something like 80 is the equivalent of 8 lots of 16, because 10 is the number that comes after 0F. Just like in the decimal system, where 9 is 9 lots of 1s, and 10 is 1 lot of 10s with no lots of 1s. The important thing to remember is that 80 is 8 lots of 16. So things like this 6F, you've got 6 lots of 16 plus 15. So it's a good rough way of figuring that out. The largest number in hexadecimal format in a byte is FF, which is 15 lots of 16 plus 15, which equals 255. That's the largest number that can be represented by a single byte of information. For those of you who don't know, a byte is 8 bits, which is a combination of 8 ones or zeros. The smallest number that can be represented by a single byte of information is 0, and the largest number that can be represented by a single byte of information is 255. So what we're interested in now is figuring out which part of this message is related to the tachometer, because all of this here is not going to be needed to display something simple like a value for an RPM gauge. So typically a lot of this information comes in pairs of bytes, so 2 of these numbers will be representing this speed of the engine. As you can see, it's in 1,000 revolutions per minute, so obviously you get 1,000 all the way up to 5,000 RPM. This probably came out of a diesel. So anyway, what we want to find out is which pair of numbers ties in to that tachometer information. So to do that, we're going to create our own CAN message, and we're going to create it from scratch. So let's go to the custom information creator here. So I'm going to start by adding in a bus. In this case, as we said already before, we're using CAN bus 0. The ID for this message, quite important, is that we're using a hexadecimal number format. So 0x, because if I put 308, it would read it as 308, but obviously the hexadecimal number for 308, which you'll remember we worked out using the online calculator earlier on, was 776 as a decimal number. But just as long as it knows that it's looking for the 308 message in hexadecimal format, that's fine. Remember from before that the length of the data part of the message that we just looked at was 8 bytes. That's 8 of those pairs of numbers and letters that makes up a number of a maximum of 255. So for each of these pairs, let's start off by just entering them all as 0. So we want 8 pairs of the number 00. So 1, 2, 3, 4, 5, 6, 7, 8. 8 pairs of the number 0. The last thing is the trigger. So the trigger is going to be when do you want this sent. So we want this sent every 10 milliseconds, which is the standard format for the fastest kind of CAN message that you can send. So 10 milliseconds delay for each message means you're getting 100 messages a second, which is really rapid when you think about it. So there we go. So the last thing to do would be to enable this message. So now I am sending a 308 message to this display, and it's saying 0 on everything. So obviously it's not going to give you any information on the tachometer. What we now want to find out is which of these individual numbers sends that information in here. Now, normally CAN messages have information in pairs. It can be different, but typically a pair gives you quite a high resolution number. So you'll have what's called the most significant byte and the least significant byte. So when it's in that kind of format, it's not really clear which one's going to be first. So you get 2 formats. You get little endian and big endian. So big endian is also known as Motorola format, and that is where the most significant byte comes first. Intel is the little endian format, and that's where the least significant byte comes first. Does any of that matter? At the moment, no. So if you want to look into more detail on that, again, plenty of information on YouTube about it. But all we really care about now is figuring out which numbers affect this information here. So we're going to start by sending random numbers and seeing what happens. So if we change the first number to a value, and I'm just going to call it 10, because we know that it goes 0 to F, then 10 is the next number along from 0 to F, becomes 16. So first number, sending 10, did nothing. Let's see what happens when we do it to the second number. All of a sudden, we see that the tachometer information jumps. So now we've had an effect on the tachometer. Let's have a think about what effect we've just had. We know that we've entered the number 10, which we know is 16 as a decimal number. So when we're thinking about is this the most significant byte or the least significant byte, we want to think about how much of an effect it's had. So just by entering the number 16 out of 255 possible then we know it's had a big effect on the tachometer. So what that basically is saying is that we found probably the most significant byte, the one that has the biggest effect. So if this number is storing the larger amount of information, then if we think the next number up from 255 would be 256, then what is 16 lots of 256? Well, funnily enough, that's about 4080, which is exactly what's being shown on the tachometer. So let's try changing it to, I don't know, 5. All of a sudden it's a lot lower. Change it to the number, this will be confusing, the number B, which as we know would be the number 411. So 11 lots of 256 is a little over 2800, which you can see is the number that's being represented on the display. So we know that we've found the number now that clearly represents the most significant byte, and it's not been scaled. We'll come on to scaling later. So now we've identified the most significant byte of that message, we want to try and find the least significant byte. That's the one that's going to do this smaller units. So to work that out, let's start by entering a known figure into the most significant byte. So we know that the hexadecimal number 10 is 16, and that 16 lots of 256 is going to be about 4080, so there it is. We know that the first byte doesn't give any information to the tachometer, so because the second one is the most significant byte, it's fair to assume that the third one will be the least significant byte. So we start entering a value, and I'm just going to enter 60 into the tachometer display now. So 60 appears to have moved the value up by about 60, so that might be an indicator that we're on the right track. If I enter FF, which is the largest hexadecimal number, then that's going to be about 255. So you can see it's increased now to 256 times 16 plus 255, which is around 4,350. So we've now successfully identified the most significant byte and the least significant byte of the RPM information. So what have we learned about CAN messages? Well, we know that the information is broadcast across a particular data bus. We know that the information appears in byte format. It's usually presented as hex numbers. We've looked at what hex numbers are and how we can calculate them into decimal numbers. We've seen that they typically contain 8 bytes of data. That's 8 pairs of letters or numbers that make up a number between 0 and 255. We've seen that those 8 bytes of data can contain signals. Those signals could be individual bytes, but where they're in pairs of bytes, they could either appear in big endian or little endian format. And finally, by adjusting the values in an individual CAN message, we've been able to identify a signal, and we've been able to figure out which one is the most and which is the least significant data bytes. So we have been able to successfully decode that signal within that CAN message.